Hello, welcome to lecture 2 on mathematical reasoning or logic. We looked at statements in the previous class. Statements, we defined statements as unambiguous sentences. We looked at two operators and or, and or, and we looked at the users also. We looked at the symbols. I'll keep reminding you of symbols that you need to take care of, because it's not possible to remember these symbols the first time you look at it. So we'll keep using it and you'll remember it. You'll just get used to it, that's it. You don't need to memorize anything. And in this lecture I'm planning to introduce a few more symbols, but before that let me clear a technicality that concerns with OR. The English language is quite a mysterious one, and we use OR in two different ways actually in English. In maths we'd like to straighten things out, so let me show you what I mean. Say that there are two statements. Every student in the class has studied either geometry or trigonometry. Now by this statement, what do I actually mean? Just in basic English, every student, if you pick a student at random from the class, he has studied either geometry or trigonometry. But if S is some student in the class who had studied both, then I wouldn't say that my statement is wrong. So both can happen at the same time. So if I give it to you in the statement form, so if P is a statement and Q is another statement, and P or Q, if I am looking at the truth or false value of P or Q, if P and Q both are true, so if P is true and Q is true, then P or Q is true, right? If both are true, then P or Q is true. Essentially what I mean is, when you use OR in this way, there is a possibility of both the events occurring at the same time. So that is one case we have, as opposed to we use OR in some other way in English also. So either, this is another example, either you get a score of at least 33, or you flunk means fail, FLUNK means fail, the examination. So just look at this case. Is it possible that both statements can be true? Is it possible that I got a score of at least 33 as well as I flunked the examination? Well, if that is true, then it will be very bad for me, but it won't be true, because this is the point I'm trying to make. We use OR in two different ways in English, but for mathematics we'll always choose this OR, as you might be used to this already. OR essentially means, so P or Q, if it is true, it essentially means that either of the statements are true or both are true at the same time. So this is the OR we'll be using in mathematics. This is not what we use. This is something else. We call it exclusive OR. You don't have to note these things, because exclusive OR is something we learn in later computer science and later higher maths. And this means that if both P and Q are true, P exclusive OR Q would be false, right? Either one can be true. This is something to take into account. We will always use this OR, just remember that. So now that we have some basic knowledge of and, or, and making statements, and a little bit of rigor, let us try to convert a few English statements into mathematical ones. So Ajay, this is one example. Ajay and Meena are above 6 feet, or I should say heights of Ajay and Meena are above 6 feet. So how do you convert this into mathematical statements using the symbols we already have? So I'll do this for you, and let us see what I mean by converting it into statement first of all. So I have a symbol for and, so I know I can replace this with a symbol, and are above, we obviously we know a symbol called greater than in mathematics, so we can use the symbol, and Ajay and Meena will keep it as such. So I'll say height of Ajay is greater than 6 or 6 feet if you want to be specific, but I'll just write 6 now. And so this is and I'll put these in brackets because I'll have to denote somehow that this is a single phrase, right? So you'll have to read this first and then and height of Meena is greater than 6. So does this do justice? Does this symbol do set of symbols do justice to the statement we already made? So when will the easiest way of checking it would be whenever my symbol, the statement, I'll call it, just for now I'll call it two different names, but these aren't two different things. So I'll call this A and I'll call this A bar, because this is not actually a different statement, but I'll just call these two just for me to spell it out. So when A is true, A bar should be true, and when A is false, A bar should be false. Then we can easily conclude that A and A bar mean the same thing. Does that make sense? So just try it quickly. Pause the video and try it quickly whether A and A bar have the same values for true and false. So how do we do that? Well, if A is true, that means height of Ajay as well as height of Meena is greater than 6 feet. And that means A bar is true as well, right? And if A bar is true, then the same thing. And if A is false, that means either one of these guys' height is not greater than 6 feet, or I'll say less than or equal to 6 feet maybe. We'll come to these negating later, but in general you should understand how to say that when a statement is false. So how to falsify a statement. So that means these two statements are same, because height of Ajay or height of Meena, if it was less than or equal to 6 feet, then this statement also will be false. So the false value also matches, true value also matches. So these two statements are correct. So I'll just call these A, both of these A, right? So we have converted the statement into symbols. Let us look at more examples now. If we do more and more examples, things will clear out. Call of Duty, the game Call of Duty, and GTA 5. Hope you are all familiar with these terms, because I assume this is what people are playing nowadays. I'm not very young, as you can tell. So Call of Duty and GTA 5 are 60 FPS games, right? The frame rate is 60 FPS. So how do you write this as a mathematical statement? I hope you have tried. So I'll write it this way. Call of Duty, let me just call it COD, because that's the shorthand everyone uses. So COD is 60 FPS and GTA 5 is 60 FPS. Pretty straightforward, right? So this is, according to me, this is a better way of writing mathematically what we mean by this. Okay. So what next? Let us look at one more example which will lead to actually the introduction of more notations. So what if I say that all students in the class, I'll say in my class, understand Hindi, right? This is my new statement. I am interested in writing this in symbol form. So all the students in my class understand Hindi. So with the symbols we already have, say that we have student 1, student 2, student 3 in our classes. Could I say that student 1 understands Hindi, student 2 understands Hindi, and student 3 understands Hindi, and student... So S1, if I called it student 1, understands Hindi, and S2 understands Hindi, right? Hindi, and S3 understands Hindi. So each of the students have the same property. But this is very tedious. And when you have, now that I have a finite people in my classroom, I'd still be going through with everything. But say that we had infinites of something, we had infinite number of something. So for that we have introduced a notation called for all. So this is the notation which means for all. So this is just an inverted A for all. This is just an inverted A for all, or this means for each or for every. So all this is symbolized by this little symbol here. And if we use this symbol at our disposal, for all, for each, for every, so for all students in my class, they understand Hindi. This I can write down mathematically. And a little symbol I will be using for belongs to, which I'll not formally introduce because I think you guys are used to this symbol. So whenever I say x belongs to integer, so I write this symbol. I hope you have seen this symbol somewhere. If not, then you guys let me know. I'll take a separate 5-minute, I'll add it to one of my lectures for this symbol. But I assume belongs to symbol is quite used to in when you're in high school, you already have seen it. So x belongs to integer means x is a part of integer, right? And you use belongs to, you read this symbol as belongs to. So using these symbols, how do I write this as a mathematical statement? So all students in my class understand Hindi. So no matter what x you pick from my class, so for all x, for each x, for every x in my class, so belongs to class, I am calling this class, this is my class, right? I am just calling this class. What is the property that x has? X understands Hindi. So do you see now how useful this symbolization, usage of symbols is? Because this is way more informative in way little number of symbols we have than this, right? So this is what I meant by unambiguity and rigor. So for all x belonging to class, x understands Hindi. X has this property that it understands Hindi, or they understand Hindi, right? This is so. And another thing to notice is this and is somewhat generalized to for all, and hence the symbols are pretty similar also. There are a lot of ways of looking at things. So even if some person in my class does not understand Hindi, this statement won't hold true as suggested by this and. So For all is just a generalization of and. So one other example for this, and this one we looked at in the previous class, but today we are interested in writing it as a mathematical statement. All parallelograms are trapeziums. Quickly now try this. I hope you have tried. And what is the class from which we are taking elements? So parallelograms is the class from which we are extracting elements. All parallelograms are such and such. So being a parallelogram is being an element of the class. So for all P in parallelograms, right, or for all P belonging to parallelograms, what happens? P is a trapezium. So do you see how much more indicative the second statements are? So this is the mathematical statement. Okay, and now I'll do the other way around. I'll give you a mathematical statement. You'll have to guess what is the logical English statement that's being implied. So say that I'm giving you this: for all x belonging to prime. This is not a very good way of writing, but I don't want to bombard you with more notation, so I'm writing it this way: for all x belonging to prime, that means for all prime numbers x, root x is irrational. So what is the corresponding statement in English we are trying to look at? So this is example number, I think 7 or something. So what is the corresponding statement in English? Hoping you have tried already. This can be read as for each x in prime, for all x in prime, or for every x in prime. So I can just say for every prime number p or x here, x root x is irrational, right? This is in English. Or even a better way of putting, a more usually spoken of way of putting it would be every prime has an irrational square root, right? Has an irrational square root. Okay, this is just in plain English. So it's all, I'm teaching you this because it's also very important to decipher all these symbols. And this is also why I am taking this chapter first, because throughout mathematics, throughout high school and college mathematics, you'll be looking at these symbols, and then as we go get deeper and deeper into maths, these symbols would be everything you communicate with, and basic knowledge of these is very important then. Okay, so now what else? Let me just give you a very proper statement in math, and let me see if you guys can deduce what does it mean in English. So there exist, okay, I'm sorry, I haven't introduced. So let me introduce the symbol, and let me introduce the new symbol first. The need for new symbol again is for this symbol, and I had an analogous symbol called OR, right? So naturally for this for all symbol, I should have some analogous symbol which is a generalization of this OR, right? And let us look at one of the statements we made, it is right here, and deduce that symbol starting from this statement. So for all P belongs to parallelogram, P is a trapezium, right? For all P belongs to parallelogram, P is a trapezium. So from this, there's a new question I'm going to ask you. How do we prove that if I am making this statement, say that Ishwar makes this statement, right? How do you prove that Ishwar is wrong? How do you prove? How to prove that I am wrong? So what am I saying? I am saying that all parallelograms are trapeziums. To prove me wrong, one would give me a well, the simplest instinct would be by basic logic we have, it would be to say that for all parallelograms P is not a trapezium. So let me write this down. All parallelograms, I'm abbreviating parallelograms by this. All parallelograms are trapeziums, and a logical way of proving this guy wrong who's saying this is all parallelograms are not trapeziums. But if you think about it, this is a way stronger statement than what we actually require to prove this guy wrong. So if guy 1 says this and guy 2 brings up this, then guy 2 has to go through a lot of work to prove that all the parallelograms one could think of are not trapeziums. Even if guy 2 could find a single parallelogram that's not a trapezium, that would prove this guy wrong, right? So in proper step by step, if you look at the logic, even if you could find a single thing that does not obey the property of being a trapezium, then this guy automatically is proven wrong. So what I mean is, for all P something happens is my statement, there should be an analogous statement such that there exists a parallelogram such that P is not trapezium. Well, this is not important for us, but what is important is this symbol right here that we introduced now. I said, while writing it, I said there exists, but you could read this as one could find, or there exists some parallelogram, or there exists one parallelogram, right? All these are the meaning of this there exists symbol. So can one look at the similarity between the there exists symbol and or symbol we looked at then? So if Mohan or Sohail went to the movies, even if one of the guys, if Mohan or Sohail went to the movies, to prove this thing otherwise, or let me take and now, because we are trying to get to or, right? So if Mohan and Sohail went to the movies, like this statement, for all P, because for all and are somewhat similar we saw. So if Mohan and Sohail went to the movies, then to prove that this person who's making the statement is incorrect, either Mohan or Sohail, if we say that they didn't go to the movies, then that person is proved wrong. So what I mean is, if Mohan didn't go to the movies, then this is incorrect. Similarly, if Sohail didn't go, this is incorrect. even if there exists a person among Mohan and Sohail who didn't go, then this is incorrect. That's what I meant by this symbol, there exists, and its similarity to or. So now we have another symbol at hand. Pause the video if you are a little bit confused, go through it again if you want, think about it, and we'll do an example now anyway. So I'll stop with this examples because I think I'll stop with this example. I'm exceeding the time limit. So I'll give you a statement, you'll have to convert it to plain English. There exists a trapezium. Now I'll just change the statement. Trapezium T, right, T, such that T is parallelogram, right? So now in the previous class we saw that for all parallelograms P is a trapezium is a true statement. This is true, this is true. So this statement which is the exact opposite of the previous statement has to be false. You can just verify it, pause the video and verify it quickly. We'll go through this in the next lecture. This is something called negating a statement, which is very interesting. We'll go through it in the next lecture, but for now I'm just trying to give you just an idea about it. So this is false, and now the statement I am making now, there exists a trapezium T is a parallelogram. So first you'll have to convert this into English, and then let us just see whether it's true or not. So converting this to English, what do we get? So some trapezium, there exists a trapezium T such that was a very very loud truck, sorry. So there exists a trapezium T such that T is a parallelogram, means there is some trapezium, maybe one, maybe two, maybe several, but at least one. So I could also write at least one trapezium is a parallelogram, right? So I hope you're convinced that this is the exact translation of this symbolic statement. So this is in symbols and this is plain English. So now if this is true or not, let us quickly verify. Let us see. So is there any trapezium that's a parallelogram? Well, so a trapezium, what's the rule for a trapezium? That opposite sides, at least one of the opposite sides, so are parallel. So can this be a trapezium? Well, yes, this is a trapezium, but this trapezium, you look at it, opposite sides are parallel, but I also draw the other opposite sides parallel. Nobody asked me, I cannot do this, so I draw this parallel and this turns out to be a parallelogram. So this statement turns out to be true. Right. And we'll, as we go further and further in our lectures, we'll get more concrete idea of why this is true, this was false, and this is also true. Maybe these two statements are alike, they are the same, and whatnot. So now finally I'll leave you with this. I'll leave you with a final example. Right. This is the ultimate rigorous statement, right? There exist, this is how statements look like in mathematics. There exists R belongs to R. This is R means real numbers. This is just a notation for real numbers, such that R is equal to 2x. So is this statement, first of all, do you understand this statement, and then whether this statement is true or not. So there exists R in R. What does that mean? So some real number or at least one real number or there exists a real number. So all these are the this part of the statement I am converting to English. There exists a real number, such that what? It is the twice of, okay, I wrote down 2, I'm sorry, this is not x, sorry. So equal to 2r. So this is, what does this mean now? There exists some real number such that it is the twice of itself. R equal to 2r means it's the twice of itself. The twice of itself. And this is the same thing. You can copy paste this here also and here also, right? So at least one real number exists such that it is the twice of itself. There exists a real number such that it is the twice of itself. Some real number is the twice of itself. Yes, right? So this is what this statement and symbols means. So I hope you understood these things. There are quite a few notations I introduced, so you can rewatch the video if you want. These are the notations I introduced today: for all, there exist, belongs to, and we also talked about a general idea about disproving someone, which is quite interesting to me, and we'll carry it forward in the next lecture. So thank you, we'll meet soon.